Good morning, everyone, and welcome back to Foundations of Algorithms. Very excited to see all of you today. And as with every week, we have our historical figure up today. This is Commodore Grace Hopper, U.S. Navy Rear Admiral, born in 1906 and died in 1992. And the big thing that she contributed to computer science was the notion of machine-independent programming languages. So if you think back to some of the movies you've seen, you might remember seeing these very large computers. And one interesting fact about those computers is all of them had their own ways in which they were designed. So they might have their own system for representing numbers, their own system for representing letters, and this means when you wrote code for them, the details of the programming language you wrote would often be specific to that particular design of computer. That have different places to put memory. So when you say, oh, move my memory to this location, you'd have to know which particular locations that designed computer would have. Now, Grace Hopper's big idea was, well, we can come up with something that can abstract all of that away. Perhaps if we have some higher level programming language, then we can have a program that sits in the middle and translates whatever the user wrote into something that makes sense for that particular machine. Now, in modern computing, this is what we know as our compiler. But if you look at the details of a modern compiler, it has kind of two parts to it. It has a front end that allows you to specify what the incoming programming language is, and then it often has a back end that allows you to specify what kind of machine language it spits out. And depending on the specific details of the chip of the computer on which you intend to run your final output, you're going to pick a different back end. So whether that is like an M-series Mac chip or whether it is an Intel processor, those are designed differently. They have different places to put things for temporary memory. And so your compiler is going to abstract away all of that detail. And that was Grace Hopper's big contribution, was really this notion. Now, one thing that's kind of interesting today is some people are saying, well, maybe AI is the latest version of this. Right now, you have to worry about also the front-end language, so whether you're writing in C or in Python. But perhaps the notion of having a large language model to translate your intent down to that next level, down to that high-level programming language, and then a compiler to convert the high-level programming language into the lower-level language that actually runs on the machine, perhaps that's the new paradigm. We will have to wait and see. Now, one other thing that I want to point out about Grace Hopper was that she wrote the compiler for the A programming language. And that might make you think like, well, if we're in this class learning C and she wrote A, whatever happened to B? Well, B is a programming language as well, and I'd encourage you to go out and after this class, explore the world of programming languages. Each of them have their own interesting design trade-offs, and in fact, one of the languages that Grace Hopper's ideas heavily influenced is one known as COBOL. Now, you may not hear about this a lot, but deep in the world of computer science, COBOL is still a surprisingly important programming language, not because programmers tend to care about it on a day-to-day basis, but because COBOL is still used inside a lot of banks and ATMs and university systems that were all created during the 1980s, and it would cost more money than is worthwhile to actually go and reprogram it in a modern language. So in past years, I used to say, well, if you want a very well-paid career as a programmer, becoming a COBOL programmer is actually a good way to go because no one else knows it, and there are very high-value systems that still use COBOL. These days, with the advent of large language models, maybe that pathway is going away a little because the large language models speak COBOL as well, but there are still jobs there at the time being. So let's now think back to where we ended up last week. So reach your memories back. I know it seems a long time ago, but we were talking about binary search trees, binary trees, and how they could be used to create priority queues. And the whole idea of a priority queue was it would allow us to select from many possibilities of potential things that we could take out of our data structure, the highest value one to pick next. So if we had different items, different students, and we were trying to pick them out in order of date of birth, we could insert them in any order into our structure, and then our priority queue allows us to pull them out in order from oldest to youngest. So we might imagine that we could do that for all kinds of things where we might have some kind of priority of allocation. So not just who is there first, but who do we think deserves it the most? And so in this case, we can use it to allocate tickets to Taylor Swift's next tour. And I will let you decide by what priority we should do it. Maybe we should do it by order of grades or who's attended the most. We can determine what should be the kind of priority that we're using for our queue. And to use that to get to Taylor Swift, we're going to need a few more ingredients. So the first thing I want us to think about is how many degrees of separation are there between all of us and Taylor Swift? Or to be a little more specific, between you and Taylor Swift, or you and Taylor Swift, or you and Taylor Swift. And by degrees of separation, I mean, how many people do you have to go through in terms of knowing to get to her? So for example, Devansh might know Professor James Bailey, and Professor James Bailey knows Enid Blyton, and Enid Blyton knows, I don't know, who's a very famous person, knows Barack Obama, and Barack Obama knows Taylor Swift. And so we count how many jumps we had to do in order to get to Taylor Swift. And so does anyone actually have in their mind already a way to get from them to Taylor Swift? Do any of you have a way, do you think? Anyone in the room? No? Have a think for a second. Who's the most famous person you know? And who's the most famous person that they know? Someone have a way? You don't have to be certain. Okay, you've had a second to think about it. But what I'll have you do now is put up the number of fingers for how many links you think it would take. You don't actually have to know the path, but just a guess. Like, is it going to be 7 hops from you to Taylor Swift? Is it going to be 2 hops from you to Taylor Swift? How many do we think it is? 5, 20 hops to Taylor Swift? That's a lot of hops. 2 hops to... Do you actually know?
I mean,
Wait a second, let's get you a microphone. I will be very impressed if you're 2 hops to Taylor Swift.
I guess if meeting a celebrity at like a meet and greet counts as...
Okay, who's the celebrity you met?
I met Post Malone at like a meet and greet thing.
And you actually exchanged words?
Yeah, barely.
We'll count that. Okay, that is 2 hops. Remind me your name? Shamir to Post Malone to Taylor Swift. Can we have a round of applause? That's amazing. So we got 2 hops to Taylor Swift. So anyone who said more than 3, you're definitely wrong, because now all of us know Shamir. Shamir knows Post Malone knows Taylor Swift. So now all of you are 3 hops from Taylor Swift. So the best that I could do on my own before Shamir was a maximum of 4. And we'll go through how we might actually check this. So in fact, this is a data structures problem, and we're going to introduce a new data structure that is particularly good at solving this kind of problem. So should we use a binary tree? Let's take a look at our binary trees and think of what this would mean for the structure of relationships. Okay, so here's a binary tree. I really should have put Shamir in here. But instead we have some folks in the class. We have Marvel, Luke, Mel, Lily, Ashley, Sarah, Liu, and Roma. And so many of these people are missing today, which is very disappointing. This always happens. But you can see only some of them know each other. So for example, Luke knows Ashley. Luke, do you know Ashley? Ashley, do you want to wave? Okay, now you know Ashley. Luke is sitting next to Sarah, so that's a definite link. Sarah might know Liu, who is also not here today. But we've got these kind of set relationships. And one thing you'll notice here is that the arrows are directional. So Luke knows Ashley, but Ashley doesn't know Luke in this picture. And so this kind of like binary tree structure doesn't seem to encode quite all the relationships that we might want. So, well, we could modify our binary tree to keep track of these sorts of relationships a little better, because at least in our class, if you know your friend probably knows you. So we could add backward links from everyone. So now Luke and Sarah know each other. It's not just a strange kind of one-way thing going on there. But still, this doesn't really capture it, because I would hope that Luke knows me, and yet he only has 2 friends. He's got Sarah and Ashley, which doesn't seem quite enough. And Liu doesn't only has Sarah, so that's a pretty lonely existence. So from this point, we need to relax our binary tree rules a little bit. Now, does anyone who doesn't already know the answer have a guess of how we might do this? What could we add to this? Shamir, you've got the microphone.
Would it be just even more pointers out of each person to whoever they know?
Yeah, so there's no reason to limit ourselves to 2 pointers from every node. I mean, that was the rule for a tree, but we can certainly go further than that. So let's relax the rules a little and create a structure where there are pointers from anyone from like each individual to anyone that they know and vice versa. So now you can see that Luke knows Roma, Marvel knows a whole bunch of people. Very popular is Marvel.
Marvelous.
Yeah, marvelous. I like that. But now because we have these bidirectional kind of relationships, let's just take the arrows, the sides of the arrows off to simplify things. So this is what we are going to call a graph. It is just like a tree, except a tree is really a specialized form of a graph where each node can only have 2 links. But in a full graph, each node can have as many links as it wants to different nodes. So this is a graph which allows us to see that really a tree is just a special case of a graph. Now, one piece of terminology that's going to be important here is a graph has kind of 2 components in computer science. It has nodes, which are in this picture, all the people, and it has edges, which are the links. And we want to talk about these separately because we want to be able to say, okay, Roma is a node in the graph. What are the edges coming out from Roma? To whom does she have relationships? But I think our graph is missing something. Who is the most popular out of everyone in the class? So I'll give you a hint. It's not actually on the picture. Who's the most popular? There we go. So, of course, everyone knows me. I'm the most famous in the class. But if we want to get to Taylor Swift, I'm not probably good enough. I mean, we had Shamir's links, which were excellent. But I used to sing in a singing group in which Mark Platt used to sing. He is Ben Platt's dad and also a well-known movie producer. And then Mark Platt directed a movie with Meryl Streep, and then Meryl Streep acted with Taylor Swift. So then we've got our provable link of 4. But now we've done much, much better. So I'm so impressed that we found that link. So this is great. But now we need to figure out, like, by looking at this, you can count how many steps it takes to get from everyone. But we're in a computer science class. We want to be able to do this algorithmically and not just the way a human would do. Just like we had that thing with sorting where, like, if you're a person, you can kind of look and see what the sorted order is. But a computer has to start at one place and look at one or 2 nodes at a time in order to figure this out. We need some algorithmic method of doing this. So how to algorithmically get the degrees of separation between any individual in the class and Taylor Swift. So let's start with a set of vertices, which will be another name for our nodes, and that's also common terminology, so either a vertex or a node. So let's call this set of vertices V, and the set of edges, the set of relationships, E. So we have 2 key methods that we're going to do to get through our graph and figure out degrees of separation. So, technique 1, let's go deep. Okay, so starting at Marvel, look at all the relationships that Marvel has. So that is Luke, Ashley, Lily, Mel, and Dr. Connie. And then from each of those people, go in order and look at all of their links. So next up is Luke. And so from Luke, we have Sarah, Roma, Ashley, and Dr. Connie. And out of all of those people, take the first one that we saw, which was Sarah, and look at all of Sarah's links. So that's Lou, Roma, and Dr. Connie. Let's say Roma is the first in that list, so that gives us energy drinks and Dr. Connie. We hit energy drinks as the first one we pick, and that's a dead end. So let's mark it that we've already seen it, and let's go back. Okay, next up, we'll look at Dr. Connie coming from Roma, and then we get to Mark Platt, to Meryl Streep, and then to Taylor Swift. So if we counter how long that took us in this instance, it took us 7 kind of edges. We can exclude the one to energy drinks because that was a backtrack, but this doesn't seem to have given us the shortest path from Marvel to Mark Platt. The idea of this search is that each time we see a new node or a new vertex, we're going to look at all of its neighbors, everything it's connected to directly, and put all of them on a stack. And then to the next step, we're going to pull the top thing off the stack and do that same process again. And we're going to repeat that process until we see the node that we're looking for. So that was an effective technique for exploration, but it wasn't quite getting us that shortest path that we wanted. Okay, technique number 2. Instead of trying to go really deep, so if I see my friend and I'm going to see my friend's friend and then that friend's friend and then only go back after I hit a dead end, let's instead try and go broad. So this is what that would look like. Let's start at Marvel again and look at everything that Marvel is connected at. And then, morning, and then let's look at everything Marvel is connected at. Then we will go through Luke to Sarah, to Dr. Connie, to Mark Platt, to Meryl Streep, and Taylor Swift. And so what we're going to do this time is we're going to look at all the neighbors first. So before deciding to go the next level of depth down, we're first going to evaluate all the neighbors. So the idea here is to put each node, instead of in a stack, we're going to put it into a queue. And then we're going to do the same thing again, extract the front item, add all the neighbors, and then extract the front item, all the neighbors, etc., etc. And what this is doing is it is prioritizing breadth over depth, because we're looking through all the possible neighbors instead of picking the first neighbor and then that neighbor's neighbor and then that neighbor's neighbor, and then backtracking. So this enables us to check first everything at that next level. So we're checking all the things 1 hop away, then all the things 2 hops away, then all the things 3 hops away, rather than going 1, 2, 3, 4, 5, 6, 7 deep, and then going 1, 2, 3, 4, 5, 6, 7 deep to another 7, and then 1, 2, 3, 4, 5, 6, 7 to another 7. So the main difference here is, do we decide to go as deep as we can first, or do we go in kind of like layers and look at everything each layer away? And so it turns out for our degrees of separation problem, this kind of layer-based approach is really good because it enables us to check each of those possible answers. Is she 1 hop away? Is she 2 hops away? Is she 3 hops away? Rather than going down random rabbit holes. But that random rabbit hole method is useful for other sorts of tasks. So what we've done now is from linked lists, we've gone to binary trees, which are like the next more general, and from binary trees, we've gone to graphs with some restrictions. And then what we can keep doing is abstracting away these different data structures. So from graphs, you could go to higher order data structures as well. And this is kind of the pattern we can go down to at least ask, okay, what are the different properties we get each time we go out a level of abstraction? So now let's talk a little bit about graph representations. So just like we did with linked lists and with binary trees, we had a representation that we could use in an actual program in order to use it in our code. So one option, actually I'll ask about this one. Who haven't I heard from this semester? Yeah.
I think I'll first try and build the tree, that binary search tree we learned, and try to somehow link the trees together.
Okay, so have a bunch of trees.
I'm not so sure.
That's not a terrible idea. That's a good start. So what did a node have for our binary search trees? What was inside a node?
Each node had 2, left node and right node.
Yeah, and in a graph, do we just have left and right?
We have more nodes than binary tree. It's not restricted to having 2 nodes.
So what's one way you might handle that? So we could change what a node is, right?
Yeah.
What would you put in the node?
We can put an an array to make it have more.
Great, yeah, you jumped ahead. So this is the silly way of doing it, is we can add link 1, link 2, link 3, link 4, link 5, and just create lots and lots of different variables to handle each of the links. But what's the problem with that approach?
There's like a lot of repeated, like you're appending, like you're adding like a lot of nodes in the data structure, and it's not very efficient.
Yeah, there's some kind of like code smell going on there because we have repeated code. Morning. We have repeated code, which indicates to us that perhaps there's a more efficient way of doing it. And you actually said right before what a better way of doing it is. We could instead have an array or a linked list of nodes that are connected to any given node. Now, an array is useful, why? As opposed to putting a linked list in it. What's the nice thing about using an array?
Array can have different data types, and linked list can only have items of the same type.
Not so much. Arrays, remember, are only a single data type, but arrays are a lot easier to handle. But Cindy, you were right that arrays are a good way of handling this, but arrays require us to set aside memory ahead of time for how many relationships someone has. So let's say we make the maximum array size in a node the most relationships that someone has. So think of your most popular friend. How many people would you guess that they know?
Like more than 100?
More than 100? And how many people would you guess you know?
Like 50.
50, okay, so that's double. So if we set aside the array to be the maximum number of friends, for each average person would be wasting like 50 slots because your most popular friend has 100, but your average person only has 50, which means that inside each of these nodes, we're wasting a lot of space for all of those extra pointers. So this is why we might use a linked list instead. Thank you very much, Cindy. Okay, so there's our better idea. This is much better than the one where we try and create enough variables to store every relationship. We're used to, when we have multiple things of the same type, we're used to using an array or a linked list in order to kind of store them within one parent data structure. So this is great, and this naturally results in a table, in another representation of just writing this out for our own sake, of something that looks something like this, which means for each given node, there is going to be a linked list at that node. So Marvel will have a linked list, Luke will have a linked list, Mel will have a linked list. Each of them has a linked list, and that linked list will contain all of their friends in the class. So let's draw that out. And let's say that Marvel is node number 0 overall, or friend number 0, and his linked list is going to have a link to Luke, and then Luke's node in Marvel's list of friends is going to be attached to Mel, and Mel is going to be attached to Ashley, and Ashley is going to be attached to Lily, and Lily is going to be attached to Dr. Connie. Now, the thing here is that that list of Marvel's relationships does not indicate that, for example, Mel knows Ashley. Number 2 does not necessarily know number 4. This is the linked list of Marvel's friends. If we wanted to know who Mel knows, we'd have to go to Mel's linked list, and we could see that she has a link to 0, which is Marvel. She has a link to 1, which is Luke. She has a link to Lily, which is 5, and a link to Dr. Connie, which is number 9. So this is one nice representation. And you'll notice that because we're representing human relationships, which are, at least in this class, hopefully double-sided, every node is going to appear twice. So for example, Marvel being connected to Luke means that Luke is going to be connected to Marvel as well. So if we look at Marvel's linked list, it has Luke, which is number 1. If we look at Luke's linked list, it's going to have number 0, which is Marvel. Makes sense. Okay, so if we follow this kind of representation with a linked list, we can figure out how long breadth first search and depth first search are going to take. So if we are going to look at someone's friends, or someone's neighbors, what is the maximum number of neighbors that any person can have? If there are 50 people in the class, how many friends in the class can you have at maximum? 49. And so if the number of people in the class is n, that is n minus 1, which is big O of n. Okay, and then each time we visit a new person, how many new options of people are there to go to? Well, it's n minus 2. And if we keep doing this, what we're going to get is we're going to get a complexity of both for breadth first search and depth first search, our two techniques. We're going to get the big O of the number of nodes plus the number of edges. And this is because we're going to have, if there are fewer edges, if there are fewer relationships, there are just going to be fewer people we need to visit. Likewise, if there are few people in the class, there are going to be fewer people we need to visit. And we are guaranteed that our processes, both breadth first search and depth first search, trace each relationship line only once. So at worst, they're going to go down a relationship, figure out there's a dead end, and come back and never go down that dead end again. And so because we're hitting each thing only once at most, we know that the big O is going to be just the sum of going through this entire set of people. And this is for the adjacency list representation, which is what we call our data structure that we've just created, where we have nodes for everyone, and inside each person, we have a linked list of all the people that they are directly linked to. But if we go back here, the way I've depicted this on the board also makes it look like another type of data structure. A two-dimensional... I can see a few people mouthing it, a bit louder. Two-dimensional matrix, array, yeah. So that could be our other representation. Rather than representing our links as a set of linked lists, we could instead just write out the big table version of it. So let's write out the big table version of it. And perhaps this is a slightly clever way of arranging all our links. So let's have two axes, and on one axis we'll have everyone's names, and on the other axis we'll also have everyone's names. And then for anyone who knows each other, let's go to the cell. So for Dr. Connie and Luke, let's look for Dr. Connie is row number 9 over here, and Luke is number 1. So in cell 9,1, let's put a 1 because they know each other. What about Ashley and Mel? Ashley and Mel do not know each other in this example. So we go 4, 2, there's nothing there. We can put a 0 in there. And for Lily and Mel, let's put a 1. You can see 5, 2 is set to 1. So let's fill this out. But now our runtime for our algorithms is a little different. Now we actually are going to end up with a v-squared runtime, because we're going to need to traverse the matrix, which has v by v rows, or the dimensionality of the matrix is v by v, which means we're going to get a v-squared runtime because there's no faster way to traverse through all the links, because for every person, we're going to need to go through the entire row to figure out to whom they're connected. We can't just skip to the ones because we don't know where the ones are in their row. So we're going to go iteratively through the matrix. Okay, we want to see everyone to whom Sarah is connected, so let's start at Sarah and Marvel, now Sarah and Luke, now Sarah and whoever was third, and go through that entire row. And so in this representation, we're actually going to get a v-squared runtime, or an n-squared runtime if we're using n to represent the number of people in the class. Mostly in the real world, we're going to use adjacency lists. Why might we actually use the matrix representation sometimes? Does anyone have a thought of why we might use this even if our two search operations are more complicated? This is a hard one, so I will, Devansh, you can take a go at it.
It's the thought that if you could find a way to store, like normally when you store an integer, even if it's just 1 or 0, you're going to be storing it still as usually like a 32-bit number. But if you were to find a way to store a matrix of that on an agency and I forgot what a matrix was called exactly, but if you find a way to store that, where each thing is only a bit, it will be very space efficient, perhaps.
Yes, so you might be able to find some way of representing this rather than as a matrix by using actual integers and storing things like that. And that is a very nice approach that I was actually looking at this morning. Some other reasons you might use it is because we can do matrix multiplication now pretty efficiently with dedicated chips. And so if you're doing an operation that involves a convolution or a multiplication over the elements in the graph, you might use that. And another reason you might use it is, remember there was a distinction between a v plus e and a v squared and a v squared runtime for the graphs. So if our matrix is very dense and the number of edges is approaching and the number of links in our matrix is very high, we may actually end up with some more efficient algorithms that can run on the matrix representation, because we already know that most of those spaces are being filled with ones. But that's somewhat beyond the class, so I wouldn't worry about it too much. So what about implementations of all of this? In the whole rest of the semester, we've been showing you code demos for everything. We've given you linked list ops. We've given you tree ops. So let's go back and let's think back for a minute. The whole point of this was really to get close to Taylor Swift. And if we want to get close to Taylor Swift, we're going to have to think about how much social capital it will take us to spend in order to end up in the room with her, which is ultimately our goal, right? Shami is like, yes, I want to get back with Post Malone, and then you leverage that to get back to Taylor Swift. And so one way we could represent this is the amount of social capital we have to spend in order to traverse a certain friendship and get them to hook us up with that next person. You know, when you're doing like, when someone asks, oh, can you put me in touch with this friend? Like, how close am I to like that person they're asking me to put them in touch with? How much capital will that cost me? That's the idea here. So for example, it doesn't take very much to get from Mel to Ashley, to Lily. That's a relationship that only takes 1 point for either of them to spend to get to the other. But from Lily to get to Marvel, they don't perhaps know each other as well, so that takes like 50 points of social capital. And so this changes what we actually want to do to get close to Taylor Swift, the kind of algorithm that we're going to want to use. What we want to do is not figure out the fewest number of hops, but the smallest social cost that we're going to have to pay. So in this case, if you look, there are a bunch of different ways still to get to Taylor Swift around the place if you are Marvel, and the cheapest route might not be going through Mel. And so we can have 5 minutes now, and I know it's a little early, but we will start again at 9:50. Once assignment 2 is in, there's going to be no use to the lecture tokens, but I hope you guys still like fill them out and get them, just for the sake of seeing who can get the most points.
I don't think the lecture's not out.
They're not?
No, I'm getting 404. Oh my God.
Let me look at what happened. Oh, you're right, it timed out. Okay, shouldn't 404 anymore. It's cut. How's everyone doing at this point in semester? Yeah, as expected. But hopefully some of you got a nice break with the Canvas downtime. Which of you hacked Canvas? So a fun bonus story that you get because you're in person is that when I was, yeah. It's not working? Why didn't you tell me earlier? Okay, it's possible I copied it wrong. So maybe we'll delay another minute so I can still give you the bonus story. I have to do the whole octa thing. Octa. I'll fix the lecture token. Quizzes. This is week 10 token. Oh, I put in the wrong code. I think I put in the one for next week. Oops. PE5, FP5. Okay, try this one. Okay, welcome back everybody. And now we're finally there. We've done it. We have our private audience with Taylor Swift and Post Malone. And Shamir is bringing us all along. Thank you very much. You're covering the bottle service as well, right? Yes, that's a yes. End of semester party. You think the Science Student Society throws a good party? Wait till you come to our Taylor Swift Comp 102 party. Okay, so we've got our audience with Taylor Swift, but now she's playing us this new secret song that wasn't even played at the Eras tour. And we want to know, like, what notes is she playing? So that, how many people here are musicians or do music? I see at least one hand at the very back. I've got a few. Ashley, what do you play? Violin. Devansh? Piano. Piano. Anyone else? What other hands? Oscar? Trumpet. No one else plays an instrument? Shamir? Guitar. Okay, so we've got a few instrumentalists in the room, and you might have seen some of this stuff before. So if we want to figure out what notes Taylor Swift is playing, one way we could do that as a human is by having really good oral skills training. Oral skills meaning like ear skills. And listen to the notes and try identify what chords are being played in the background. But that seems like a lot of work for some of us computer scientists who aren't as musically inclined. Although I will tell you my first degree was a music degree, so perhaps not me. So one thing we could do is we could check the recording, but the recording of whatever it was that Taylor Swift just played doesn't tell us what the notes are, it's sound. Okay, so we'll have to do something else. Well, that gets me to thinking, like, how do we even store the music on the computer in the first place? Would it make sense to store it as like a character array? No. What about a bunch of integers? I mean, we could. It's not a totally stupid idea, but we're going to need some way to figure out like what it is we're actually storing. If we store the letters TAYLOR SWIFT, that's not going to sound really good when we try play it back as music. So what about physicists in the room? Do we have any physicists? Only Oscar. Has anyone taken Physics 1? No one else. Okay, we've got Mel. Finally, this is your moment. I'm going to run a microphone all the way up there. Okay, Mel, tell us, how does sound work?
Sine waves and vibrations.
Okay, tell us a bit more. Stay away from the sound waves. Tell me a bit, sine waves. Tell me a bit more about the vibrations.
They oscillate up and down.
What oscillates up and down?
The air.
The air, okay. And inside the air is made up of?
Particles air, oxygen.
Yeah, we've got vibrating molecules at different speeds, and then what happens? So this is maybe a bit of bio. Have you done any bio? Okay, but you've like existed as a human. Okay, Lily's gonna help us out.
It vibrates your eardrum, and then your brain can essentially translate the vibrations into like auditory perception.
Okay, that sounds pretty good. So vibrating air molecule, what determines what we hear? What about the air molecule?
How much it's moving.
What do you mean, how much?
Like the rate of its vibration.
Rate of its vibration. Okay, so we've got a bunch of different things. We've got rate, we've got size of the displacement. What does the size of the displacement often do?
It affects the level.
It affects the volume. This is great. Lily, you were just what I needed. So one thing that we can do is we can measure how much the molecules move in a given space of time. So let's make this time, this is for Mel back again, delta T, right? And we're used to doing this from physics. So what gives us, what is velocity?
Distance over time.
Distance over time, so delta
X over delta t.
delta x over delta t. So we could do this, and then the other thing we can do is we can turn that into a wave and measure the amplitude of the wave. So this is getting back to some of what Lily was telling us about before. I'm actually going to go down and play this note. And while we're there, Lily, this is a task for you to figure out what note this is. In fact, I'm going to see if I can sing the pitch before I've even played it. So I think this will be something about... Anyone hear a perfect pitch? Disappointing, but I'm going to play that sound for you. Not bad. That is A440. And I was bang on, so I'm super proud of myself. So perfect pitch, for those of you who aren't aware, is where someone tells you what note they want you to sing, and then you can do it right off without having to hear an example of it before. Anyway, so I'm going to give myself a big pat on the back for being able to produce an A440 without reference. And so one way we can represent that is as a wave like this, where we have a measurement of displacement or amplitude over time. And then what we can do is we can actually look at an instrument and figure out where that pitch might be on the instrument itself. Now, obviously, instruments' waves do not sound quite as pure as that note that we just heard, and that's because the physical construction of the instrument is going to impact the shape of the wave and then give it its timbre, its kind of quality that we hear about it. And so if you play an A on the piano, hopefully it'll sound much nicer than that kind of that we heard before. I guess my voice doesn't really sound like the sine wave either. So what we've done here is actually measure the displacement at different intervals. And so you'll notice that I have these individual dots, and these are values we can actually store. There we are. We have little dots that we're storing at given time intervals, and these we can actually store. And if you were to count how many cycles of the wave there are per second, how many peaks and troughs, you would get 440, which is equivalent in physics, we call that a hertz, a hertz measurement, which is how many per second measurement. And so that gives us our 440, which is the note used on a piano in an orchestra to tune the rest of the orchestra. That's called A440 because it's the note A at 440 hertz exactly. And if you look at music history, you'll see a number of different variations having developed over time. And in non-Western musical cultures, they also have different tuning systems that are not necessarily centered around A440. Just some fun little musical stuff. So if you compute the distance between the peak and the trough, that's 0.0022, and so 1 over 0.022 is about 440.5. So that's roughly right here. And so if I were to play a concert A on the piano, it's not going to look quite this clean. We'll in fact get a waveform that looks a bit more like this. And what we're going to call our delta t is our sampling rate. It's how often do we actually do these measurements of what the molecules are doing in order to figure out how frequently we should store numbers. So when you have these MP3 files on your computer and it says, oh, it's an MP3 file recorded at 44,000 hertz or 48,000 hertz or 92,000 hertz, what that's telling you is how frequently it's, for what intervals is it storing these numbers. And that's also going to make the file size bigger, because if you are generating 98,000 samples for every second of music, that means you're going to have to store 98,000 numbers for every second of music. But this is an example of, let's say, our chord that Taylor Swift, or what Taylor Swift was playing at a given time. And the problem here is that this is not like a single sine wave like we had before, where we can just count the distance between the peak and the trough and figure out what note it is. We're going to need to do something substantially more sophisticated. Now, Does anyone just happen to know off the top of their head what we're going to do? Luke? Fourier transform. Yeah, we're on a roll today. So this looks like a mix of different waves. This is what we use a Fourier transform for. One of the things we'd use a Fourier transform for is to decompose a complicated wave pattern into its constituent wave patterns. So how much of this note is there, plus how much of that note is there, plus how much of the last note is there. And typically in music, we're going to use combinations of 3 to 5-ish notes to create what we call a chord, which is a particular sort of sound. So this is a mix of different waves, but also a mix of waves with very different amplitudes. So some notes might be played louder than others, and you can see that partially because the spacing of the numbers that we've captured is very different, and they're at very different heights. So some of them were captured very, very high, and some of them were like close together and close to 0 or close to each other. And so this is actually going to make our task of handling this algorithmically quite a bit more complicated. So we've got a couple of ways that we could try and store them. We've got a couple of different numeric types in C and in computers in general that we could use. So what are the different numeric types that you remember from programming this semester in C?
Numeric types.
Yeah, things that can store numbers.
Like data structures? Or
Not even data structures. Like, you remember that char is like a type and that stores characters. What are the ones for numbers?
there's like integers, floats, doubles, like is that what you
Yeah. So if you were being asked to store how high one of these dots is, what would you use personally?
probably doubles? I don't know how. I see 0. I don't see 1 on like the scale.
Yeah, we can go back a little. We can go to here. And why would you personally choose to use a double?
They have more like precision than floats. And they have like decimal points.
And they have decimal points. And what are the different things that you think are important to factor in? Like, what do you care about when you're picking which type to use?
Whether it like represents it accurately. So you need decimal points.
Yep, accurately. What are some other things that one might care about, whether you personally care about it or not?
Size.
Size?
Yeah, I guess.
Okay, so let's take a look at some things that we might want. We want our results to be correct or correct enough for our use case. We want efficiency, which you said, both for memory but also for time. So inside the computer, there's circuitry that handles integers differently from floating point numbers, and the floating point ones are typically slower. We might also care about how easy it is to implement. Like if I've given you 20 minutes to write your code, you might pick integers over floats because integers are less annoying. You might think about effectiveness. So at the end of the day, for the thing I care about, is the type that I'm using going to actually do a good job of the particular task, regardless of how accurate it is in truth? Is it predictable? Like if I do an operation over it, can I guess easily what it's going to do? Okay, so when we're thinking about our particular task of representing numbers for music, we've seen that we're both going to have numbers that are fairly widely spaced apart, but also numbers that are very, very close together. And so we're going to want a numeric data type that can handle both of those. So when numbers are very, very close together, we're going to need more precision because the 5th, 6th decimal point is going to matter a lot. But when they're really big, what we need is the ability to scale. And then maybe one other thing that we might want is we might want them to be as accurate as possible. But do decimal numbers have like an endpoint? Like, is there a number of decimal places after which you're done? Christina? So let's say 1 divided by 3. What is 1 divided by 3?
Like 0.3 repeating.
So is there a point at which we have achieved perfect representation? No. And so if we want to be able to scale to whatever precision we want, we're going to need to use some fancy data structures or some fancy mathematics one way or another to make that happen. So there are a whole bunch of different things that go into our recipe of figuring out which particular, how should we design our numeric types so that they're the most effective for the task that we want, and in this case, that's representing music. So one thing we could do is take integers and just multiply them by a fixed amount. So let's say that we had a picture of our graph over here. We could just use integers to represent it, and let's say our number is 0.055. What could we multiply it by to make it an integer?
100, I think.
Yeah, we could multiply it by 100. So multiplying by 10 would give us 5.5, and by 100 would give us 55. And so we could figure out, okay, how many decimal points do we want to deal with? Let's say we want 10 decimal points. And so let's just multiply all the numbers by 10 to the 10, and then we've got integers. Okay, that's one strategy. What might be some problems with that?
That like overflows an integer, I think.
So that would overflow our integer types. So we might not have enough bits to deal with it. Oscar has something he wants to say as well.
If the decimal is small enough, it might just round back down to 0 or 1.
Yeah, so if our decimal is really small, if it's more than 10 decimal points in size, then we'll end up getting a 0, which is also not good, or we might get the opposite where it gets rounded to 1. So we have some problems with this technique for music. So what would be a way of being like slightly fancier if I allow you to store 2 numbers instead of 1 at a time? For every dot, you're allowed to store 2 different numbers. What could you do? So remember, technique 1 was just multiply them by the same, multiply every number by the same power of 10, and then it gets converted to an integer. So for every number you can store 2 things, what could you do instead?
I guess you can try like scientific notation.
You're on the right track. So give me the idea.
Yeah, so you have like the power like for the second number, which tells you like by, okay, if the number's like AB, it's like A times 10 to the power of B.
Yeah. And so what you're doing there is you're saying, let's have the significant digits, and then on top of that, let's have a scaling factor. And that scaling factor is going to be like times 10 to the whatever. And so you're getting very, very close to what we actually do. So we could use integers and multiply by an amount stored in a second integer. Or what could we do if we only want to have one place where we're storing everything? So the idea you just had was, let's create 2 variables. In one variable, we'll store the significant digits, and in the other variable, we will store the scaling factor. But then we have 2 things. So what could you do if you don't want to deal with that?
You mean like abstractly deal with it? Like,
Yeah, I don't want 2 things. I don't want to have 2 things to keep track of, but I still like where you're going with this idea of having the significant digits and the scaling factor.
just like wrap it in a struct, or
Kind of like that, but we can be even smarter. Because we're the ones designing the type, we're designing the programming language, what can we do? You're really, really close. Should we give it to Luke?
sure.
Okay, let's pass the microphone down.
I was just going to say you can write it as like the logarithm of the original.
That's a good idea as well.
Kind of encodes both of those in just one number.
So both of you have really super interesting ideas on the right track. But what we can actually do, because we're in charge of how the programming language works, is we can create a new type. Let's call it a float, or let's call it a double. And the way that's going to work is we'll have some number of bits, let's say 32 bits, and inside those 32 bits, we'll save some of the bits to be the scaling factor, and some of the bits to be the significant digits. And what we can do is we can have a marker that tells us how many of those digits are going to be used for the scaling factor and how many of those digits are going to be used for the significant digits. Oscar, you have something.
Isn't that already how most floats work?
That is indeed how most floats work. That's where we're going with this. It's trying to understand why floats work that way. And it works exactly because of the problems that Christina indicated for us, and that Oscar and Devansh indicated for us. I don't remember which one of you two brought up the problems before. But what we can do is use this idea of scaling to encode the information that we need inside a single set of bits. And this gives us what we call floating point numbers, where we have the scaling factor actually embedded within the number. Now, the other type of number with decimal points that we can represent is a fixed point number. And this was like our first idea of scaling, where we had one number by which we scaled everything up and down by. So that's where the decimal point is really, you can think of it as being in a fixed place, and then what we just do is we shift everything in one direction to kind of scale it up. Whereas with floating point, because the scaling factor is variable, that really means that we're moving the decimal place around based on the number itself. And there are different places where we might want to use these. So we've already talked about some of the ways that this can go wrong, where we might lose precision. So in finance, for example, we're going to use fixed point operations because we want a certain type of predictability. We're going to say, okay, any amount under 0.0001 of a cent we're not going to care about. We're just going to do rounding because those numbers are small enough. And so fixed is going to give you tight accuracy within a specified range, and you're going to get deterministic error bounds as a result. This is also going to allow you to do certain kinds of mathematical operations in a predictable amount of time, which is going to become important if you're doing cryptography, because an attacker could look at how long it's taking you to compute something and guess what number you're computing on based off of that. So that's where we might use fixed point. Floating point, on the other hand, is really useful for things like music, where we're going to need really big dynamic range because we want to be able to scale to really loud volumes and really quiet volumes. And we're going to want to be able to store that in an efficient way, to not necessarily need an arbitrary sized number of bits or complicated bookkeeping to keep track of that. And where you're not going to be able to predict the scale of intermediate results is another place you might want that. And here, it's also important to say that this is going to introduce some errors in, because we're only going to store a certain number of significant digits based on what we're doing. And so errors will creep in, and we'll see some examples of that both later in class and in some of the exercises you give. But for example, in music, if the error is very, very slight, that's not going to change the waveform in such a significant way that your ear is going to be able to detect the difference. And so it's actually going to be okay and quite efficient to use floating point numbers for representing music. Now, I used to say that, computers have a lot of memory, and so we don't actually need to use floating point, even though we have in the past. What we could do is just represent our music with more precision, take a little bit more memory. But in today's world, and particularly over the last few years, floating point numbers have come significantly back into fashion because of one of these bullets over here in particular, machine learning. So all of a sudden, being able to very efficiently represent both large and small values has become much more important again, because these are used for the weights of neural networks, which, as you might remember from your assignment 1, are what actually drives this whole large language model paradigm. And so our representation of floating point numbers is going to just follow exactly what Christina was telling us before. Inside the number, we're going to use the first digit that we store. The first bit is going to store the sign. And if it is a 1, it will be a negative number. And if it is 0, it will be a positive number. The next set of digits we're going to call the mantissa, which is really just a fancy way of saying the significant digits. And then after that, we are going to store the exponent. The b, we're always going to use the same base in our case. And this is the recipe for how we're actually going to store floating point numbers and doubles in C. So we're going to call this number the 2 to the power of whatever the exponent is, the characteristic of the number, and we're going to call the sign, and then those significant digits we're going to call the mantissa. And I actually don't know, maybe we can look up in the next break where the word mantissa comes from. I'm not actually sure. But this leaves us with a question. So remember, older computers from when I was growing up were all 32-bit, and now we use 64-bit. But this leaves us with a question of, well, how many bits should we save for significant digits? And how many should we save for the scaling factor and for the characteristic? This is going to be quite an important choice, and it's a choice that is debatable, like there's not a single right answer. And so one of the things that you'll encounter in your computer science journey is the notion of standards. These are agreed upon conventions that everyone uses. And in the case of floating point numbers, the most prominent standard is one known as IEEE 754. IEEE being the International Electrical and Electronic Engineering something or other. I don't remember what all the E's stand for, but they are a peak body for professionals in electrical engineering, and they like claiming computer science as well. I have some thoughts about whether I'd want them to do that or not, but anyway, they set the standards on floating point numbers. And so what did that standards body with all the professionals agree on? They said for floating point numbers, for floats in C, let's use approximately 24 bits worth of precision. And then for doubles, let's use 53 bits. And this is the precision we're going to get from the mantissa bits. So now let's actually do some examples of writing this out. And it's going to take a couple of steps. Okay, so write out the significant figures in binary, and we'll get how to do that soon. Normalize it so that only one significant figure is to the left of the decimal point, and then multiplied by a power of 2. Then in the third step, encode the significant figure directly as m, and a 1 in binary is going to be implicit because in IEEE, as long as the number is non-zero. S is going to be the sign of the overall sign of the number. So if it's a negative number, we're going to put a 1. If it's a positive number, we're going to put a 0. And then what we're going to do is we're going to bias the exponent. So that's going to allow us to encode, that is going to determine the size of the scaling factor. And so we're going to say, okay, set 127 as the base point, as our equivalent to 0. And then what we're going to use E for is E is going to modify how far away that is. And that's just going to allow us to make efficient use of those bits. So calculate what I plus E would be, where I is just this 127 baseline, and then add the actual scaling factor, which is E, and then write that all down as the last few digits. Now this is a bit complicated, so we are going to divide it up into steps. So the first step is to figure out how to convert fractional numbers into binary, because I haven't told you how to do that yet. And we can use this little algorithm here, and we're going to draw it out by hand in just a moment. But the basic idea is do repeated multiplications by 2 on the fractional part, separate out the leading digit. So take the first digit and just write that in the final representation. And then take the remainder and repeat this process. So this sounds a little abstract, so let's actually work it out. Okay, so let's take the number 0.625. This one is a little easier because there is a 0 out the front, so we don't need to worry about the whole number part of it yet. So let's just start with the decimal part. Now our algorithm was multiply the whole thing by 2. So what do I get? Get 1.25. And we have a 1 out the front. So let's write a 1 down in our final representation. So now what we do, we take the remainder, everything else, we take the other digits, and we multiply that by 2 again. So what's 0.25 by 2? 0.5. And there is now a 0 out the front. So let's write a 0 in our final representation. And now we multiply by 2 again. So we take the remainder and multiply by 2. 0.5 by 2 is 1. Thank you. And now we have a 1 and no remainder, so let's write a 1 down in our final representation. And that gives us our final representation. We put a 0 and then a decimal point, and then we write it out in binary. 0.101 is 0.625. Okay, let's try another example. This is 0.175. Okay, what is 0.175 by 2? .35. So we have a 0 as our first leading digit. 0.35 by 2. That's another 0. Now 0.7 by 2. We have a 1. And now 0.4 by 2. And we have another 0. 0.8 by 2. We have a 1. 0.6 by 2. It's 1.2, so we have another 1. 0.2 by 2. It's a 0. Oops, I forgot to write that out. 0.8 by 2.
You're repeating? Yeah, it's repeating.
Oh no. So because we've ended up repeating, what we're going to end up doing is capping ourselves off at our precision. So however many bits we have, that's going to determine how many of the significant digits we can write. And this gives us an indication of where some of the loss comes from in this representation, because we can keep writing this out just like we would with 0.333 recurring. And this also tells us something interesting, which is that different numbers will be representable or non-representable with a finite number of digits in a different base system. So this is going to, even though 0.175 is easily representable in decimal, when we get to binary, we're going to end up with this problem. So here we have just a couple of examples of this process, and you can also reverse it by looking at what each of the digits represents. So just like we looked at for integers, we have in base 10, have our ones column, which is 10 to the 0, our tens column, which is 10 to the 1, our hundreds column, which is 10 to the 2, etc., etc., or in base 2, it would be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. For decimal numbers, we're just going to do the opposite, where we have 2 to the negative 1, the 2 to the negative 1's place, then the 2 to the negative 2's place, then the 2 to the negative 3's place. So that's the halves column, the quarters column, the eighths column, the 16ths column, as we go further and further down our decimal number. Now let's do 14.5 as a full IEEE 754 floating point number. Okay, so let's start off with the bit for the sign, that S. How are we going to write that? Is this a positive number or a negative number? It's a positive number, 14.5. So we're going to start off with a 0. Now we've got to figure out how to write 14. So 14, the process we can use is we can do the opposite of what we were doing for the decimal numbers, and instead of multiplying by 2, we can divide by 2 and take the remainder each time. So let's do that example with 14 first. Here we go. So let's take 14 and divide it by 2. 7, remainder 0. 7 divided by 2. 7 divided by 2 is 3, remainder what? 1. Now 1 divided by 2. There we go. And so then we're going to do one more division of that to get our final 1, I think. That's 0, 2, 4, 8. Yeah. And so now we can read it off and we get 1, 1, 1, 0. Now we do our 0.5, which is the opposite rule, which was multiply by 2 and take the digit, the leading digit. And so we have a 1 after the decimal point, and there we have our representation of 14.5. And so now we can take this representation back over here, and that is going to be our mantissa. And we now have our exponent, which we're going to need to figure out how to scale, how many decimal places we want to scale this such that only the leading 1 is before the decimal point. So we are going to want to shift 1, 2, 3 decimal places along so that we get 1, 1, 0, 1, and the decimal place will be there. So in this case, our exponent is going to be 3. Because if you were to take 1.1101 and raise it and multiply it by 2 to the 3, that would shift it along back 3 places. And that would get you the 1110.1. So now we're ready to write that out. We have our sign, which is 0. We have our mantissa, which is going to be just 1101. Why? Because the leading 1 in IEEE 754 is implicit. They don't require you to actually write it down as part of the number. So unless it's all zeros, if the number is all zeros, then it's a 0. And otherwise, we save a bit by just assuming that that first 1 is always going to be there. Because we know if there is value in the number, then that'll be a 1. And then we write down our E. So in this case, E is 3. But remember, we have the bias, which is 127. So we calculate 127 plus 3, which is 130, which in binary is, anyone know off the top of their head? So 128 is 2, 4, 8, 16, 32, 128 plus 2. So we are going to have a 1 in the 7th place and then a 1 in the 2nd place. So let's write that out. If we have 8, if we're storing this in 8 bits, for example, there is a 1 in the 2nd place, 1, 2, 3, 4, 5, 6, 7, 8. And there is going to be our representation. And let me look at the version I prepared earlier to see if we got this right. Now let's take a look at actually seeing this representation produced by a C program. So we have 2 programs now, int bits, and I will start with float bits. Float bits is going to show you the bits in a floating point representation. And here we're going to use a function that you've probably never seen before called ATOF. And what this does is it converts a string representation of a floating point number into an internal floating point representation. So it would take, like, if you were to write the characters 14.2, it would convert those characters into a float type that you can then use. It's like A to I, except this is A to F. So it's characters to float. And what we're going to do here is something also pretty sneaky. We are going to take the results of our floating point number and create a pointer to it. So what is uval? Uval is going to be just an unsigned chunk of memory. And we'll talk about what that means soon. Then what we're going to do is we're going to figure out how many bits are in this and repeat a loop going through all of the bits of our number. Now here we're about to do a very fancy trick that's going to require some new content. So now I'm going to take us over here. We need a few more C operations in order to actually write code that allows us to peek at the bits of a number. That's showing up correctly? Yes. And these are as follows. The shift left operator, which is going to move all the bits one place to the left. The shift right operator, which is going to move all the bits one place to the right. We are going to have an operation which allows us to check between two different sets of bits, whether the bits are the same, different, and in what places. We are going to have a new operation called XOR, which returns true if only one of the bits is a 1 in the two that you're looking at. And we're also going to have one final operation called a NOT, which just flips all the bits in a single number. So if a bit in the number was 0, it becomes a 1. If the bit was a 1, it becomes a 0. So let's sketch out the operation of these on a sample table pretty quickly. So looking at the operation of a shift left. So let's start by writing out 12 in binary. How do we write out 12? What is 12 in terms of 16, 8, 4, 2, and 1? 8 plus 4, right? So we're going to write 1, 1, 0, 0, and then a 0. And shifting all of those bits left one place is going to give us 1, 1, 0, 0, 0. And so if we recompute that, now we have 16 plus 8, that's going to be 24. And so what did that operation essentially do to the number? It doubled it. So in base 2, if you do a shift of all the bits to the left, that's equivalent by multiplying it by 2. Just like if you were to shift all the digits over in a base 10 number, you'd get a multiplication by 10. So then what do we expect our right shift to do? The opposite. This is just going to be divide by 2. Now, one kind of thing to note here is that the way the operation works, at least in C and in the hardware level, is if there are bits that would fall off the end. Let's say we only have a 5-bit number. If we were to do a left shift by 3 of 12, that would take this one out the end over there. And so what C is going to do is it's just going to drop it. And so what we would get is this number, which is just 1. And so in that case, the divide by 2 analogy is not 100% correct because it doesn't account for the limited width of the integers. And so that was with a right shift. That was with a right shift. A left shift is going to do the same thing, just on the other side. So if we right shifted it twice, we would end up with 16 because that is the highest we can go in a 5-digit binary number. Now let's look at the operations which operate on 2 numbers. So let me write that out a little cleaner. Let's say we have these 2 numbers A and B. These are just example numbers. Let's take a look at the different operations that we might do with them. A bitwise AND asks, do both of the numbers have a 1 in each, and ask that question successively for each position. So in this first position over here, do they both have a 1? No, so we get a 0. Do they both have a 1? Let me rub that out. Do they both have a 1 in the first position? No. Do they both have a 1 in the second position? Yes, no, 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 no. And so bitwise AND yields this outcome. A bitwise AND is written as an ampersand in C, and that is our AND. Now we also have an OR, which is written as the pipe symbol, and this asks, do either of the numbers have a 1 in that position? And so we would get 0, 1, 0, 1, 1, 1, because in the last few, you didn't need both of them to have a 1 there anymore. A single one of them having a 1 was fine. Then we have a fun operation, or I think it's fun, called exclusive or XOR. And this is similar to OR, except if both of them have a 1, it still returns a 0. So we could write this out in our little table over here. If they both have a 0, it should be a 0. If they both have a 1, it should be a 0. And if either of them have a 1, it should be a 1. So that's just another way of writing it out. So let's go and do this with our concrete number. So we have a 1 and a 1, which that is not exclusively one of them being true. And then we get a 1 there, a 1 there, and a 1 there, because in the last 3 digits, only one of them was set to 1. And then a not is pretty simple. So let's do not A, which is represented with a tilde. Not A is 1, 0, 1, 0, 0, 0, 0, 0, 1, because I just flipped each of the bits. So A used to have a 0 in the first place, so now it has a 1. It used to have a 1 in the second place, so now it has a 0. And these are considered some of the fundamental logical operations that are actually needed to build the circuitry for a computer, because we can build using using semiconductors, we can actually build devices that perform these operations on electrical wires coming in. So if you imagine that a wire coming in carries either a current or carries a voltage or doesn't carry a voltage, you can build devices that, because of the physical build of the molecules within the atoms and molecules within the electrical device, it actually performs one of these operations. And so that's why we care about them so much in C, because that's actually what our hardware is doing under the covers. And from these, you can build up the full instruction set of a modern computer, particularly with something called NAND, which is another operation which we don't include here, but this is where it is similar to a NOT, but it is kind of the opposite of an AND. So it is, as long as it is not both of them being true, mark it as true. And this is called just a fun fact, it's called a universal gate, because if you only have the electrical devices that can perform that NAND, that NOT AND, then you can build up all the other gates. And with all the other gates, you can build up arithmetic. And with arithmetic, you can build up the entire computer's set of instructions. So that's kind of a cool preview into what might happen if you did an electrical engineering degree or a computer engineering degree. You'd see more of that. But now we have enough to actually go back to our code and understand what this is doing here. What this is doing is it's taking the number 1, which is a 0, all zeros followed by a 1. And then what it's doing is it's shifting that along a number of different places. So if we were to write it out on our iPad, that would be a 1, followed by 1 and a 0, followed by 1, 0, 0, followed by 1, 0, 0 in each iteration of the loop. And then for each iteration of the loop, it's taking these and doing an AND with whatever the other number was. If this is A and that's B, it's computing an AND such that the result is only going to be positive if B had a 1 in that position. So B has a 1 in this position, so in the first iteration, we're going to get a 1. In the second iteration, it'll be A 0, 0, 0, 1, 0, and B will be 1, 0, 1, 0, 1. There's not a 1 in both of those, so we're going to get a 0. And then on the third iteration, we're going to get 0, 0, 1, 0, 0. B will be 1, still be the same thing. And now we have a 1 in both A and B, so we're going to get a 1 there. And so you can see for each iteration, it's going to be positive or true only if B had a 1 in that position of its number. Because the next time would look at this position in the B and then would look at that position in the B. And so this is what our code is doing is it's shifting that 1 along progressively using the bitwise AND to figure out what is the bit in the number that we were aiming to look at. And so if that evaluated to true, it prints yes, there was a 1 in B at that point. If it evaluated to false, it's printing no, there was not a 1 in B at that point. So now we're ready to run it. Oh, I nearly clobbered it. Now the compiler warned me. This is a good new compiler that tells you if you accidentally overwrite your C file. I'm very impressed with that. Okay, so let's run float bits. Oh, and it takes in an argument, so let's do 14.5. So let's look at what we got. We have a 0 because 14.5 is positive. Then we have the exponent, which was 130, which is the next 8 bits. So the way it's broken up is because we have that sign bit at the start, the last 0 of that exponent is actually pushed over to the next column. And then we have the 14 over there, and then our 0.5 over there. And so if we were to figure out where the decimal point would actually sit, it would sit to the left of this number 1. And so there is float bits. And this is actually, it's both fun and also a little annoying to try and get it right because it's a little finicky, but you'll get the hang of it after doing it a few times.
Purpose of the biasing for the exponent?
The purpose of the biasing, I think, is to pre-specify the range that we're going to do this in. Like imagine you want to do positive and negative exponents. And so you don't want to try and represent negative exponents by having to do the sign again. Make sense?
Yes.
Okay. So we can actually use our operations that we've just done with bits, as Devansh was saying earlier, and as he cleverly pointed out, for pretty efficient graph algorithms. So here, for example, we can quite efficiently compute which neighbors we haven't visited from a given node yet by actually using the binary representation. So let's say that we're storing which neighbors of a given node were visited in an integer. What we can do is then have a list of neighbors that were visited similarly in an integer, in an integer representation. Then the ones we haven't visited yet are the not of the visited, so that just flip all the bits in the visited. And then we can figure out which new things we have to visit very efficiently by computing the logical AND of the neighbors with the ones that we haven't visited yet. And so we can actually use this to do some graph algorithms quite efficiently. And so this representation gives us another potential speed up to some of our algorithms that relies on some of the more lower level details inside the CPU. So now we are just about through with our Taylor Swift adventure, but let's finish it off a bit with looking at other types of numbers that we might use and where we might use them. So we've gone on this adventure of figuring out how we can efficiently get to Taylor Swift as our through a path of our connections. We've figured out how to represent her music. So let's just go through the last set of numeric representations that we might need to represent all of our possible Taylor Swift problems. So the first representation of negative numbers that we can do is one called sign magnitude representation. And so this is just write your negative number the same way you'd write a positive number, but use one bit to represent the sign. And this is kind of what we were doing in our floating point numbers before. We were using one of the bits to represent the sign. You could also, in theory, do this for integers. Now, this is not necessarily bad, but there are some complications with it. How many ways can we write 0 using sign magnitude representation? Are there 5 ways of writing 0? Is there 0 ways of writing 0? Are there 1, 2, 2? What are the 2 ways?
0 and negative 0.
0 and negative 0, because you can have all zeros and a 1 at the front. which is -0, and then all zeros, which is +0. So that's a kind of a weird feature of it. This also means that if we're trying to implement this in hardware, we would need either extra hardware or extra control logic inside the hardware, because you would have to look at that first digit before deciding whether the operation should be an addition or a subtraction. And so that's a little complicated. Also, this would make comparisons slower, because you would need to test the sign bit first before either treating them as in order or out of order for the purpose of comparing magnitudes. So there are a few downsides with the sign magnitude representation. The next way we could do it is ones complement, which is take all the bits for a positive number and flip them if you want to do the negative representation. So this would give us two different bit patterns for 0 again. So this would be all zeros and all ones would both be 0, because the inversion not 0, if we apply the not operation to 0, will give us all ones. And so this would make addition and subtraction taking an extra step again of figuring out this inversion. And then conditionals and comparisons would be awkward, because we have to treat -0 as the same as +0, but the bit patterns would be sorted for every positive number. And so if we write these out, this is what ones complement would look like. So take, for example, the number 1. The number -1 is 100 is 1110. And so if you look where that appears on the circle, it's actually 2 spaces to the left, not 1 space to the left. So we have 0 at the top, -0, 1 to the left, and then +0. Did I say that right? If we have +0 at the top of our circle, that's the all zeros. The next one along to the left is -0. If we go to the right of +0, we have the number 1. And if we go to the left of -0, then we would have -1. And so on and so forth until you hit the maximum value that you can represent down at the middle. So if we were to write that out, that gives us a number circle that looks something like this. So we've seen two kind of awkward representations so far, but we want to get to a representation that actually makes implementing in hardware, doing comparisons all nice, and that doesn't have this weird like 2 zeros quirk. So this takes us to the representation that we actually use for the most part in C, and this is called 2's complement representation. And this eliminates the double zero and gets us to our kind of desired state of the world, where the further we go away from 0 in terms of the magnitude of the bits, the further away we go from 0 in terms of the distance, it gives us a higher magnitude number. And so this is going to be our desired bit pattern, is as such, and this is 2's complement, where the 0 is all 0 still, and we're essentially dividing up that number circle into half, and the further away you get from that 0 point down to that middle point, the larger the number is. So how do you actually convert a positive number into its negative equivalent? So write the magnitude out, then invert all the bits, and then just add a 1. And that's how you get your 2's complement. This is much easier than all of our prior examples, but we will still do one just for the sake of it. So let's say we are writing out the number. Let's say we are writing out the number 12. So the number 12 was what again in binary? 1100. So we have a 0 and 2 to the 0, a 0 and 2 to the 1, a 1 and 2 to the 2, and a 1 and 2 to the 3. And to get the 2's complement, what we're going to do is invert all the bits. So that would give us 0, 0, 1, 1, and then add 1. Now remember, in binary, if we add 1, we can't let a column get to 2. So what we have to do is we have to carry the 1 we get 1, 0, but we have to carry the 1. Then we have 1 plus 0 plus 1. That takes us to 2 again. So we have to carry again. And that takes us to 1, 0, 0 with a 0 out the front. Now, because we're only doing this with a small number of digits, a small number of digits in the width of our integer, there aren't very many possible combinations. So we've divided up a very small circle, but this process will work even if you say, okay, this should have been 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Let's do the 8-bit version. So if we have 8 bits to work with, the inversion is going to be 1, 1, 1, 1, 0, 0, 1, 1. And if we add 1 to that, we're going to get a similar pattern. 1, 2, 3, 4, 5, 6. I've lost track of my counting there. So 1 and 1 is 10, so carry the 1. Another 10, carry the 1. And now we have 1s in all of those places. So you can see that if we increase the width of the integers that we're dealing with, that's going to reserve more of the bits for the negative numbers on one side, which is not going to reserve those bits, I should say, is going to split the circle in such a way that there are more total numbers that we can represent for both positive and negative. Had a question about why do we add the why do we invert and then add 1? So let's look at what all zeros was. So all zeros was this in for a normal 0, so that's positive 0. And then in 1's complement, negative 0 was all 1s. And so if we want to go from negative 0 to positive 0, we can just add 1 here. So 1, 1, 1, 1, 1, 1, plus 1, we get 10, 10, another carry, 10, another carry, 10, another carry, 10, another carry, and then another carry, but now we've run out of bits. And because we've run out of bits, we just throw away that extra 1, and that takes us back to 0 again. And so with that, we have now covered all the different types we're going to use for semester. We have covered all the different ways of getting to the Taylor Swift concert, and we are going to take a short break before moving on to something very different. Okay, welcome back everyone. We are now at the last segment of today's lecture. What we're going to do now is have a bit of a step back from some of what we've been doing all along. And in the rest of today's lecture, and as well in half of next week's lecture, what we're going to start doing is think about what we've learned more holistically. So I think we have maybe one data structure left, but what we've got is a whole collection of tools now. And so what should we do with the rest of semester? Well, we could call it here, which some of you might be grateful for. And in fact, we are going to have a lot of extra just content that I find interesting that is not going to be accessible. But it is a good time for us to kind of like step back and reflect on different problem-solving strategies that we might do, or different types of problems we might solve in the world, or different interesting classes of algorithms. So kind of exposing you to the world of algorithms out there. So we could categorize all the different world's algorithms by problem type or by complexity class. So we could say all the n-squared algorithms, or all the algorithms that run faster than some polynomial, whatever that polynomial may be. Or we can categorize them by design technique. And Hanju is going to next week go through a lot of these. So I'm only going to cover one of them, and with a very particular, two particular examples. So here's the list of algorithms from Wikipedia, and you can just look this up and see all the different wonderful algorithms that you could spend the next 20 years of your life thinking about. And we can see automated planning, combinatorial, sequence algorithms. The list is going to go on and on and on and on. So having looked at all the different algorithms that are out there, we could now try and match these to different real-world problems. So what is the optimal route down a mountain? How can we match medical students with the residency programs or the specialization problems that they want to go in, given what the hospitals want? How could we automatically fill in holes in damaged photos. All of these different things we can do with careful design of algorithms. And some of these things are actually super deep and super interesting as the algorithms behind it. So for example, the medical school matching one is a really, really famous algorithm called the stable matching algorithm, which is actually used in the United States to do their entire medical graduation system. And that was an algorithm developed in the late 20th century. But we could also group by design techniques, and this is some of what we're going to do is we're going to look at the different algorithms that we've developed in this class and think about the different kinds of techniques, show you a few new algorithms that can be put together from the general principles that we've come up with, and then use those to solve a few problems that we could experience in the real world. And these are some of the different strategies that are out there and that you'll hear a lot of them next week. But the one that we're going to cover today is called generate and test. So let's take it back to Taylor Swift, because I know at least some of us in the room are fans. So generate and test could be something like generate every possible eras to a set list that follows a set of constraints. Now, for those of you who are paying attention to the structure of the eras tour, it followed a set format. There were songs that were already always in there. Perhaps let's imagine that the opening song was different each time, even though it wasn't. There were surprise songs chosen from her catalog. And then we could imagine that there were a variety of costume changes. The Eras Tour evolved over time. So we could imagine that from all the different sets of possible options, we could generate the full list. Now, why might we want to do this? Well, we might want to look for all the sets of tours, all the sets of concerts that fulfill a certain set of criteria beyond that. Concretely, the way we often solve a lot of these problems is through a technique demonstrated in a very famous problem called the knapsack problem, or the backpack problem, or alternatively subset sum. These are all different names for the same thing. And the problem formulation is a variation of variations on the following. So imagine you have a backpack that fits a set weight of items. It fits 100 kilos of items and no more. What is the closest you can get to packing the knapsack or the backpack exactly, given a set of items whose weights you know? Now, there are different versions of it. You can say, is there a set of items that'll sum to exactly 100? You can do what is the and so that is a decision problem. So you could say, is there a set of items that sum to exactly 100? You could do an optimization version of the problem, which is what is the best set of items such that you get the closest you can get to filling it. You can do an approximation version, which says, I don't really care if I've got the actual best answer, but as long as I know it's within some bound of the correct answer, that's good. And so we're going to look at one variation of this for the moment in some C code, and then look at how it can be applied to a game that many of you have probably played during some of your off time. Here is a copy of subsetsum.c that all of you can download if you like. And so what we're going to have here is an array of all the possible items that we could fit in our backpack. Here we're just listing them by their weights. And in this case, we want to find out if there is indeed a set of the items that sum to exactly the capacity of our backpack, which in this case is 1,000. Now, as I said, there are variations on this. So if you're asked for, please provide the collection, that's a slightly different problem to, is there a collection, to what is the best possible collection you can do, even if you can't get exactly there. This one is just the decision problem. And the term decision problem is going to be applicable to all kinds of different things where you're just asking, is there a solution to this problem? And maybe Hanja will talk about it next lecture, maybe, maybe not. If not, we'll come back to it in week 12 with some more examples. And subset sum can actually be solved using, or this version, this decision problem, can actually be solved using a really simple intuition. And that is, for any given item, there are only two possible worlds. The world in which it is part of the solution and the world in which it is not part of the solution. So in order to figure out whether there is a world where you get the exact the exact collection of items such that you hit the exact weight, you can create really a diagram that looks a little bit like as follows. So let's do item 1. And this is the world, we've got a world in which it's in the solution and a world in which it's out of the solution. Okay, then in each of these worlds we have to make, that is not a very good looking number 1. There we go. And then the next thing we have to decide is, in each of these worlds, is item 2 in or out? And then for each of these worlds, we have to decide item 3. And so at any given layer of this, how many nodes are there? We should know this. We've seen binary trees. 2 to the I minus 1, where I is the level. And if we have n items, what is going to be the total number of items in the tree once we've finished plotting them all out? 2 to the n minus 1. Do we care about the minus 1? So this is going to be big O of 2 to the n things that we're going to need to look at in the worst case to find the one combination that does actually sum up. So for each of these worlds, if item 1 is in it, if item 1 is in, we're going to keep track of how much weight it's added to the backpack so far. So let's say item 1 was 50 and item 2 was 25. So in the world where we get item 1 in and item 2 in, what we're going to do is look at the capacity of the backpack. Let's say it was 1,000 and subtract 50 for the next layer down because item 1 was in. And then over here, this is going to be the world where it needs to sum up to now 925. And so anything from here, it would have needed to sum up to 950 because that's the weight of the backpack minus the weight that we've already filled up from item 1. And then if we've chosen item 2, then that means in all of these worlds, we need to find stuff that sums up to 925. And so this gives us this really nice structure, but an algorithm that runs in big O of 2 to the n time, which is not very good at all. That's exponential time. So if we look at what our code is doing, it's really just this recursive approach of building out inside the computer's memory in a way, this combination, this tree structure. So let's look at the recursive, let's look at the initial call. Let's feed in the array, feed in which item of the array we're up to looking at. So are we up to checking whether item 1 is included or whether item 2 is included or item 3 is included? And then the amount of weight that we have left after the items that we've included so far. And so we have our base case inside subset sum, which is if there is no weight left in the backpack, if we're at exactly 0, we've found a case where we have exactly filled it up. Otherwise, if there are no items left to consider, but we still have weight in the backpack, then return false, because we never found a solution where there are no items left to consider and we haven't reached the exact weight, so we lose. The decision is false. Otherwise, do this recursive call. Compare both cases and compute the logical OR of them. Are either of these cases a case in which we win? So case 1 is where you include the item, so where you take k and you subtract the weight of the item we're looking at the moment. And also consider the other case, where you don't include the item, and so you leave the weight of the backpack as it was before. And so this is actually fairly simple code for what seems like a relatively complicated program, but only with the caveat that it's going to take a lot of time to run. Any questions on this one? I think this code is actually pretty elegant. I like this one. And so now, for the rest of the lecture, those of you who haven't gotten enough sleep can take a bit of a nap. And those of you who are interested can pay attention because we're now up to bonus content. Okay, what is this? Yeah. I'm glad that was the loudest answer we've had all semester. At least you are finally confident about something. So how many of you have actually played Sudoku? Is pretty much everyone? You at least know the rules? So the goal of Sudoku is every subgrid of 3 by 3 should be filled with the numbers 1 to 9 with no duplicates. Every column and every row should also be 1 to 9 as well. And you start with a partially filled in grid, and then the trick is to figure out, okay, given the constraints that we have, what can I know for sure about where certain numbers belong? And you fill it in step by step and try to fill it out. And this is kind of a fun game. I will confess that with games of this sort, I've actually personally lost interest in them now that I know so much about the algorithms, because to me it feels very mechanical. And so I've kind of lost some of the joy of it, which is a bit sad. But with all of these kinds of like puzzles that appear in the newspaper, I have a really fun time the first time figuring out the optimal algorithm for solving them, or at least the classes of algorithms that work. So we're going to spend a bit of time figuring out about Sudoku, and there are a couple of approaches we could use. The first is going to be our generate and test. So given this board, for every square, we're not choosing is it in or out. What are we choosing? Which possible worlds could we live in for every square? How many worlds are there for every square? There's 1 through 9. So there's a world where let's say, the top row, the third one along, is a 1. There's a world in which it's a 2. There's a world in which it's a 3. There's a world in which it's a 4. And for that world, you could say, okay, now let's move on to the next square, given we're looking at the world in which we guess that there's a 1. And when you play Sudoku, you probably do this. You say, okay, I'm not sure if this square has a 1 or a 2 in it. Let's imagine that there is a 1, and now look at the implications of that. And so that's one actual way to solve a Sudoku, is by doing generate and test. Now I will say it is not the best way that computer science have, but it is certainly a valid way. And what kind of solution would that give us to? So in the world where we subset sum, where the decision was in or out, that gave us 2 to the n. Where we have 9 possible numbers, what are we going to get? 9 to the n. So that's even less efficient, although big O, they're still both exponential time. So 9 by 9 grid, 9 possibilities for each cell. This gives us, if for an unfilled grid, 9 to the 81 possibilities, which is about 10 to the 77. And this is longer than the age of the universe if we're going to do this to really generate all the possible Sudokus. So probably not the best out of all solutions, but we can already start by eliminating a lot of those possible worlds, because not all of those worlds contain valid grids. So for example, there is a world where there is a 1 in position 1, 1 and a 1 in position 1, 2. We don't have to explore all the worlds that come out from that world. Like we don't have to do 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, because 1, 1 is already invalid. So we can eliminate a whole bunch of the branches. And so how much would that help? It would only take about 3 centuries to generate all possible valid Sudokus on a single core computer. There's also a whole bunch of interesting research areas on, I forget the name all of a sudden, recreational mathematics. There's a whole field called recreational mathematics that looks at games and writes interesting research papers about games. I have some friends in there. Particular one friend who now works for Museums Victoria ran a business selling buckyballs, like the magnetic little balls, and did a research project at Melbourne Uni on the different possible configurations of those magnetic balls. So kind of fun. There's a lot of fun stuff in here. And so here's this one paper I found on Sudoku, which is what is the smallest number of clues that a Sudoku can have and still have a unique solution. And so there was a computer search for what is this number? And so this is proving that there is no Sudoku that only has one unique solution with 16 clues or fewer. And so the minimum number of clues you need in a Sudoku is 17. And this is actually pretty cool. It boils down to a much more fundamental algorithmic problem called the hitting set problem, which is one of the classic problems in a problem class called NP that we're going to talk about in our very last week. Oscar.
So just to clarify, for that it would mean if you've got 16 or less clues, there are multiple solutions.
There are multiple solutions. And so you're trying to make a Sudoku for which there is only one unique solution. You can still have fun with a 16-clue Sudoku, but it's not. It doesn't have a unique solution. And this also depends on the grid size. Like obviously, if you change the size of the grid, that changes the number of clues that you need. But cool research. And so strategy 1 is to iteratively fill the board and then backtrack. So every time you find that your grid is not valid, go back up the tree and explore one of the valid worlds. And so our code looks something like this. Because we're now at a late stage of the semester, I'm not worrying about teaching you more C code. So here we have something that looks much more similar to Python code, because hopefully all of you know Python at this point as well. So pick the next space in the grid that is not yet assigned. If there are no spaces left in the grid, then you've solved it because you've filled it out. Otherwise, do a loop and check all 9 possible worlds. So fill the grid with the number that, fill this location that you're looking at with the number that you're up to. Check if that would create an invalid grid. If it creates an invalid grid, just skip right to the next number. Otherwise, run this recursively. So this is generating that same tree of all the possible worlds for Sudoku, but eliminating the invalid ones as we go. So can we do better than generate and test? This is always our question for the class. And so this takes us to a really nice class of algorithms that I personally like. I've been lecturing about this for years, but I only actually used it in a practical setting last year or last year or the year before for the first time, which was I had all these professors and I had all these classes, and I had to match professors to the class that they were going to teach based off the preferences for the professors and when they were available. And so this is a classic example of something that we call constraint satisfaction. So given a set of things to fill, and a set of options and a set of constraints that tell you the rules by which you're allowed to fill it, figure out a valid fill, a valid matching or a valid setting of your problem such that you get the answer. And so I really did use this kind of algorithm last year. No one had ever done it in the university before, and I did it for our professor class allocations. So that's how I ended up here. And so we can actually portray Sudoku as one of these problems, and in fact we can portray it as the most basic kind of satisfaction problem, which is just known as SAT, for short for satisfaction. And so there's a really nice paper on representing Sudoku as a SAT problem, which is again in the field of recreational mathematics. And so I'm going to talk a little about SAT just because it's fun and because you'll see it repeatedly as you go into more in depth in computer science, and it does form the foundations of some of the theory of computer science that you will just touch ever so lightly on in your third year. So I'm giving you third year content now because I know you're all so great. So let's come up with what we'll call predicates, statements that are either true or false. And we're going to have a lot of these statements because Sudoku has a lot of squares on the board. And we're going to create predicates as follows, these statements that can be true or false. So a predicate S, X, Y, Z, that's the index of the predicate, is going to be 1 if the cell in column X and row Y contains digit Z in the Sudoku that we're looking at, and 0 otherwise. So for example, 119 is 1 because in row 1, column 1, there is a 9, but 112 would be 0 because there is not a 2 in location 1, column 1. So you can imagine that for each of these squares, there is actually 9 predicates. And so we have 81 possible predicates for this grid. But the only ones of them that are set to 1 are 119, 128, because there is an 8 in row 1, column 2, And 3, 3, 6, because in row 3, column 3, there is a 6. All of the other ones are set to 0, so I'm only showing you the ones. And then we could write out, for our full Sudoku, we could write out all the starting assignments. And I haven't even written them all out here because there are too many, but here are some of the zeros. So 111 is set to 0, 112 is set to 0, 113 is set to 0, 114 is set to 0, all the way until we get to 119 is set to 1. And this little triangle shape that we're using there, called a wedge, is going to indicate the logical AND. And what I'm saying in this is, yes, it is true. It is the case that 111 is 0, and 112 is 0, and 113 is 0, and 114 is 0. If you take the logical combination of all of those things, that whole big combination is true. And we know that if a logical AND of a bunch of things is true, each one of them individually must be true as well. So we have these rules of logic that you can use to break apart statements that contain ANDs and ORs. And we'll actually use those in the algorithms that help us solve these constraint satisfaction problems. Now we also have the opposite to a logical AND. We have a symbol for a logical OR, which is kind of this upside down triangle symbol. And this is essentially saying, is it the case that one of these things is true? And we can say that we know some values of 121, 112, 124, 125, 126 for which this is true. For which assignments is that whole statement true? And that is a question, I'm now asking you that question. For which assignments is it the case that that logical statement evaluates to true?
Whenever the digit in like the second cell.
Whenever, what about that second cell?
Whenever there's a digit from 1 to 9.
Yeah, whenever there is any digit from 1 to 9 in that cell. And so this gives us a way of expressing the fact that every cell should be filled. We can say at least one of these should be true, and that should be true for every cell. So we could have this logical statement and join it with a logical AND to a statement that says the same thing for 111, 112, 113, 114, etc., etc. And so if we want to build up the predicate that says every square in the Sudoku should be filled, we're going to create one of these lines joined by an AND, joined by another line, joined by another AND, joined by another line for every square in the Sudoku. And so this is going to start getting pretty long. And we can write out constraints like this. This is a constraint because we're saying we don't know if this is true yet, but we want to find a world in which it is true. So we're going to write lots of these constraints that encode all the things that are necessary for a successful Sudoku completion. So let's actually look at them. I'm not going to go through them in exhaustive depth and explain them because you don't really need to know for any particular reason the constraints that solve Sudoku, but I want to show them to you anyway so you get a flavor. Because there are a lot of constraints that we need in order to encode all the information that we know about Sudoku. So here I'm using not the little triangle and not the little wedge, but big triangle, a big wedge and big upside down wedge. So big and big or, which is just saying like and this and that, or that, or that, or that, and joining them together. This is just a compact way of representing that. And so these are some of the constraints that I need. So the first one is there is at least one number in each cell. So that's where for each row and each column, do an and the lines that we AND together are a combination of ORs. So this is saying for each cell, do or that cell is a 1, or that cell is a 2, or that cell is a 3, or that cell is a 4, and then do the AND of that for every row and the AND of that for every column. And likewise, we can do each number is at most once in each row. And so the way we encode that is by saying if one of these is true, then the other one must not be true. And we can do similar things for all our other rules. So we can say each number is at most in at most once in each column. And we do that just by changing the indices around and by changing which things are ands and which things are ors. Again, you don't have to worry about the details here. This is kind of just to give you a flavor of what it looks like to try and do this. I actually did this personally myself. I didn't do it from the paper. It was kind of fun. Then we get a little more complicated with each number appears at most once in each 3x3 grid. And then you need the playing with the indices becomes annoyingly complicated, although there are ways to do it by flattening it out a little bit. And then we have some more, at most one number in each cell, because the constraint solver doesn't know that you can't have two numbers in each cell. So naively, you could think that both 111 are true and 112 are true. One of those says the number in cell 1 is a 1, and the other one says the number in cell 1 one of them says that the number in cell 11 is 1, and the other one says that the number in cell 11 is 2. You have to tell the computer that those can't both be true at once, that would be an invalid solution for the problem. And so we have a constraint that says that, and then we have each number must appear at least once in each row. It must appear at least once in each column. And then we have each number 1 to 9 does appear in the 3 to 3 grid. So we both have some of the constraints that say you can't have the conflicts, but also the constraints that say what counts as a valid solution. Okay, I think that is all of the constraints. There are a lot of them. Does anyone have a guess of how many individual clauses there are? So a clause is like something separated by an or an and. Just a guess. It really doesn't matter if you get it right or wrong. 42? 300? Other guesses? A billion? Who said a billion? A million? Okay, hands up if you think more than a million. Okay, hands up for less than a million. Okay, hands up for more than 100,000. Hands up for less than 100,000. Hands up for more than 10,000. Hands up for less than 10,000. Okay, answer reveal, 11,988 clauses. Now, there might be a way of reducing this somewhat, but at least in the version that I wrote up, that's how many clauses there are. Now, that might seem complicated, but actually it's not too bad for constraint satisfaction in our setting. But I have some bad news for you. Despite the fact that we formulated this problem in a really beautiful fashion now, it is still fundamentally hard to solve. There is no algorithm that's going to guarantee whenever you write a problem like this that there is going to be an efficient way to find the solution. So I am going to talk a lot more about this particular problem, about SAT, in our final week. But for today, there are SAT solvers out there. If I give this particular set of clauses to a specific computer program, it will probably be able to solve it and in a reasonable time. It's not because the problem isn't fundamentally difficult for a computer, but more, Sudoku is only a 9x9 grid, and so the number of clauses that we have and the specific instances of the problem we give it are easy ones. It's like I could say, well, there is a complicated set of problems, but I'm going to give you an easy instance of it. I'm going to, for example, if I give you a map of the world and tell you, I won't spoil that yet. We'll get there next week. But you can imagine there are problems that are hard in principle, but for which an easy example exists. And Sudoku, when we practically solve it, we're always working on easy examples that are what we call tractable for a computer to solve. Tractable here means reasonable to solve under reasonable constraints. So what are some of the limitations of our whole generate and test strategy that we've been using so far? There are a few reasons why it might not be good. So some reasons why generate and test is not ideal is because sometimes the solution space is really, really big. So remember when we were talking about the Sudoku, we have a branching factor of 9 for each square. And for a game like chess or a game like Go, that's even larger. And so if for any given layout of a chessboard, there are more than 9 possible next moves that you could make. So that branching factor is really large, and so generate and test on its own is not going to be good enough to solve a game of chess efficiently. In other cases, the solution space is what we call non-enumerable. You might not know what the possible set of next moves will be. You might not know all the possible answers that you could go to, and so you might not be able to generate all the possible combinations, which might make it hard. It might also be hard to figure out how to best explore the solution space. And so writing an algorithm to do it might be difficult. And then there are also some problems in the world out there for which even checking if you've got the right answer is a hard thing to do. So there are some problems in the world for which checking is easy and finding a solution is hard. Some problems for which checking is hard and finding a solution is hard. And that is going to be some of the most exciting stuff, what is my favorite little bit of computer science theory that we'll talk about in the very last week. And for that, we will leave it today. Thank you very much, everyone, and I will see you in 2 weeks.